Thank you for having me here. It's an honor. I'm Roddy from the University of Arkansas in Fayetteville, Arkansas in the U.S. And today I'm going to be talking about my active deorbiter development of a solid-state inflation balloon deorbiter subsystem for CubeSats. So just the overview of what we'll be going over. So it's system concept, and then the design overview, followed by some modeling, and then I'll get into the prototyping work that I've been doing for the last about 13 months. Lastly, I'll address the evaluation criteria and how my design addresses those. So our system concept is pretty simple. We wanted simple, low-cost, effective deorbit. This is actually verbiage from our call for papers for the grant that funds us. So we tried to figure out what is the most simple, effective, low-cost way of doing it. Looking at the options, we believe that aerodynamic drag assist is the best way in terms of simplicity. It doesn't. Furthermore, we were going to use a spherical balloon. And by using a spherical balloon, you don't need active attitude control or attitude knowledge for the design to work optimally. Propulsion systems, of course, we need attitude control and a knowledge system, and a solar sail typically needs some sort of slewing mechanism for optimal performance. So that's how we landed with inflate a spherical balloon. The next step is we're going to use a solid-state gas generator to inflate the balloon. There's been balloons that have been flown in the past, but they use compressed gas in a cylinder, which needs a valve. You need compressed gas and a valve. Those are all things with failure mechanisms. So our solid-state gas generator will generate gas on demand without the need of any valves. Basically, how it's a chip, it's a MEMS device, and there are individual gas wells that we deploy. They can be tailored to hold anywhere from nanograms to micrograms of material, thereby generating nanograms to micrograms of gas. And we can integrate tens to up to thousands of wells on a chip. So the design is very scalable and tailorable for any application. Lastly, it's low cost. Right now, we're looking at a prototype cost of around $500. The chips themselves, one wafer costs about $500 to make, but that gives you about 60 chips. So the heart and soul of the design is the solid-state gas generator, and they're pretty reasonably priced at the prototype stage. So this is our system overview. There's kind of four main components of the design. So this schematic shows, first we have a balloon, we have a package. I have some better CAD shots later on, but there's going to be an electronic control board, which is not pictured here, and then the solid-state gas generator. So for a point of reference, I'm going to refer to the entire system as the SSIB, solid-state balloon, solid-state inflation balloon, and the solid-state gas generator as the SSGG. This gets too wordy if I don't use an acronym. So this is an illustration of what the solid-state gas generator will look like. We'll have input pins and output pins, and then these are the micro wells. Inside, the system will go together thusly. The SSG is mounted on a PCB board. The PCB board will go inside the balloon, and then evacuate the balloon in vacuum conditions, fold it up, and that will go into a housing which will hold it. It doesn't have a lid or a hatch. It just has clips that hold it in place. When you want to deploy this, you activate the solid-state gas generator and deploy it with one gas bit at a time until the balloon deploys. We can additionally maintain the inflation state of the balloon over time by deploying more gas wells, either on an active basis or by incorporating a set and forget sort of timer in the PCB board. So I looked into the effectiveness of this system, and I did some modeling to do that. I've worked out a program in MATLAB that I wrote myself, and it's based on a finite difference time domain technique. I'm basically solving this derivative. So dp dt is equal to this expression where p is the orbital period. 3 pi A would be the the semi-major axis of your orbit. Rho is the density, atmospheric density. A, of course, is surface area. CD, coefficient of drag, and M is spacecraft mass. For my modeling, I'm assuming 1.3 kilograms per U. For the density, I'm using the 1976 standard atmospheric model to get density as a function of altitude. To work this, basically I set a dP. In this case, I've been using minus a tenth of a second, and then use this expression to calculate how much time did it take for my orbital period to decay by a tenth of a second. From that, I can back calculate the altitude and everything I want to know. So this is a plot of the altitude as a function of time for 3 CubeSats, 1, 2, and 3 respectively. This is assuming a 1 meter balloon. The table shows the orbital lifetime for the same 3 spacecraft with various balloon diameters ranging from 0.5 meter to 1.5 meters. Without a balloon, the orbital lifetime from 550 kilometers is something around, according to my calculations, which is congruent with other models, 94 days, that's about 25, 26 years. This model assumes a spherical object. Basically, the balloon is large and the spacecraft is negligible size in area compared to it. It also assumes a spherical orbit, independent of inclination. So the SSGG is, as I said, kind of the heart and soul, so I'll go over its design a bit. It's got 3 main elements. I mentioned the wells before. Basically, the wells hold sodium azide. Sodium azide is the same chemical that's in your car's airbags. You can think of this as a miniature version of an airbag in your car. Instead of generating, just generating far less gas, and instead of only having one deployment, we can deploy multiple times. So the microwells, represented by the blue boxes, are loaded with sodium azide. My prototypes are typically using 20 nanoliter volumes. Underneath each well is a resistive heater, which is made with microfabrication techniques. These are all built on Pyrex glass wafers. Nominal design size is 1 square centimeter at this time. Basically, the heaters warm up the sodium azide. Once it reaches about 325 degrees C, the sodium azide thermally decomposes, leaving behind sodium salt and creating dry, clean nitrogen gas. Lastly, there's these diodes, and diodes are used for individually addressing each well. So the red resistor there is driven with the port conditions that are shown. So these are my input ports, these are my output ports. I would drive this heater by applying voltage here, applying a float or a high impedance input here, ground here, and a high impedance float here. By incorporating the diodes, we can reduce the number of input pins for the device, which makes this device practically scalable. As I mentioned before, we built this with microfabrication technology. It's a MEMS device. I apologize if you aren't real familiar with that. Ask me plenty of questions if you need to. It's kind of a whole topic in itself, so I'll try to teach you as I go. So let's start with the heaters. I built things in parallel. I built heaters, I built diodes, and I built integrated SSGG, and that's kind of how it evolved. So first off, I'll talk about the pictures. This is you can't see the whole device area, but I have 4 different heaters with 8 contacts. Of course, this doesn't have the diodes in them, so it's not an individually addressed array. But I built these so I could evaluate the properties of the heaters and attempt to deploy gas. This is a picture of a heater with a well, and the white is the sodium azide crystals. The second picture is after the well has been deployed. You can see the burnt up sodium azide. I've investigated a number of different materials for the heaters. I started with Ti-copper Ti-copper. Both of those are bad because the copper is highly corroded by the sodium azide. Titanium works well on its own, but you have to grow a pretty thick layer for the resistance to be suitably low. So Ti-gold worked quite nicely. However, it burns out at a lower temperature than I like, So I stuck with type platinum. That is what I'll be moving forward with. A really nice feature of this as well is that I can drive these heaters and using a feedback loop, I can control their temperature because of platinum's RTD performance. One cool feature of this is we fill the wells using a surface wetting technique. So you can't see it, but there's a well here over each heater. The wells are created by optically transparent material. So this material, it's a polymer, SU8 polymer, and it's hydrophobic. The heaters, though, are hydrophilic because they're a metal conductor. So how we fill them up is we take sodium azide, dissolve it in water, you dip coat the chip, shake off the excess solution, and the solution will preferentially stay in the wells and run off the rest of the device. Then you just let the water evaporate, and you have a populated well. You can do this for tens or ones or thousands at a time. This is the diodes. So it's the MIN diode is a metal insulator metal diode. It's a quantum tunneling diode. It's not a semiconductor diode. It has a insulating membrane between two metals that experiences quantum tunneling breakdown above a certain applied voltage. I built 3 generations for 3 specific purposes. Generation 1, pictured here, and there's his response, essentially helped me develop the fabrication process. Generation 2 helped me refine it. There was some mechanical issues. And Generation 3 helped me track down the right insulator thickness, and the final result has a nice diode effect. This is how it's built. This is a side view. So we put down metal contacts, grow a diode, insulate the side of the diode, and then connect the top of the diode to an adjacent conductor. This is the final SSGG design. So same sort of side-by-side schematic. It's the same thing as we built the diodes. So put down conductors, in this case titanium gold, grow a diode stack, put on isolators, create the bridges to connect the top of the diode to the other conductor, and lastly make a well. This is a view of my lithography masks. So here you can see my heaters. There are my diodes. On this design, I've also included a independent test diode, so I can test the diode without the rest of the circuit. There's also a test heater here, so I can look at that. Step 3, again, insulator, contacts or bridges, and then microwells. This is a photograph. There's the test heater. This is a little hard to see, but here's the test heater, test diode, and then this is the business end of the chip. We've been looking into balloon development. Right now we've been working on just developing a fabrication scheme. The particular materials we're looking into are Kapton, metallized polyimide, Mylar, and Teflon. There's some trade-offs here. Mylar is degraded by UV, while Kapton is degraded by atmospheric oxygen. So a metallized version or some Teflon might give us some happy medium in between. But this is a prototype, that's been fabricated. It's a 1/2 meter in diameter, and basically we cut 2-dimensional structures with a laser cutter and then tape them together. This is just a prototype. What we'll be doing for real test articles is we're going to heat weld the seams to give an airtight seal. Our electronics control board is kind of laid out here. We have, it's a microcontroller-based driver system. So we have a master microcontroller. This is a schematic representation of the solid-state gas generator. And then we have a driver microcontroller and a sync microcontroller. The sync will also measure current through feedback, or before feedback, and the master controller will coordinate these things. So we'll operate in a switch mode. We'll write voltage outputs, and we'll read our power readings and current values and incorporate that with feedback. This is a picture of our PCB. It's a little bit large right now. It's 3.5 by 2.5 inches. But this is just for test. We can shrink that significantly for flight articles. Here's what you've been waiting for. This is what the subsystem cab looks like. So we'll have a subsystem frame. Inside that frame will go the balloon. And then we'll have retaining clips to hold the balloon in place. And that bolts directly on top of the in this case, a 1U CubeSat, but it could be a 2 or 3 or whatnot. What is not shown, and what I haven't talked about yet, is how to interface with the balloon from the CubeSat bus. Basically, there's going to be a wire coming out of the balloon. In when we stick the PCB in the balloon and fold it up, it'll have a tail. That tail would feed through one of the holes in the subsystem frame and interface directly with the CubeSat bus. Basically the forces that are on the balloon are insignificant compared to the strength of a serial cable. So we envision using a serial cable, but this could be changed to another protocol with trivial effort. One of the tricks is going to be how do we seal the balloon and evacuate it. We've looked into that. In short, what we're going to do is we're going to fold up the balloon and have basically an opening that goes to a valve. This whole setup will go into a vacuum chamber. We'll evacuate it down to 10 to the minus 7 or so torr, and then open that, with that valve open, and as the vacuum chamber loses air, the air will flow out of the balloon. Once this has reached a stable state, we'll close the valve, vent the chamber, and seal off the pathway to that valve, thereby leaving a sealed balloon that is completely empty of air. If we didn't do that, when we would launch this thing, there would be residual air, and it would deploy without our consent. So this structure will be quite rigid because it will have atmospheric pressure pushing on it since it's evacuated. So the leaves or the folds of the balloon will be rigid. So we don't envision a problem with this flopping around or coming out on launch. Once we get in space, we deploy some gas, or we allow these thin membranes to separate. We envision it to unfurl from here. So that's one of the things we'll be testing this coming summer, is how big do we need to size these clips so it stays in, but is also on launch, but is also able to come out on deployment. We have a test campaign planned with NASA Ames Research Center. We're going to do TVAC, we're going to vibe test, simulate launch loads, and we're going to deploy in vacuum conditions. So I wanted to address your evaluation criteria real quick. So effectiveness. As I said, for a 1 to 3 CubeSat, the deorbit lifetime is around 25 years with no deorbit assist. With a 1 meter balloon, which is my nominal design, we can get that down to 118, 236, or 335 days for 1, 2, and 3 respectively, according to my calculations. Those numbers will likely vary by up to 20%, maybe 10%, but this is still a very effective system compared to having no system. As far as our launch envelope, that CAD picture I showed you, it took up 1 centimeter of the CubeSat's volume, and of course the whole cross-sectional area of the end. So that gives us a volume of 100 cubic centimeters, and the mass is, we're looking at 50 to 70 grams right now for prototypes. The balloon thickness we're looking into is 5 micron thick polyimide, which will give us about a 15 gram balloon. So most of that mass is taken up in PCB, electronics, and subsystem housing, which we can take measures to reduce that weight. Cost, as I mentioned before, is pretty low. Excluding labor costs, I can produce a prototype for about $500, something that I can have as a real test article. Feasibility, we built prototypes of the gas generator, the balloons, and the PCB, and we've successfully gone through that development phase. So far, we've overcome all of our challenges and hurdles. We've also demonstrated that the solid-state gas generator worked in vacuum conditions and does in fact generate gas. Impact on satellite is minimal, as it's a bolt-on solution with low volume, and as I said, it's a bolt-on solution. It doesn't, as long as you can accommodate the end space on your CubeSat, you can integrate it. So for CubeSat operators, it doesn't put a lot of burden on you to make room for it. Low power budget, low mass, and low volume are what gives it low impact. Reliability. The reliability comes from the built-in redundancy in the solid-state gas generator. It'll likely take only a few gas wells to inflate a balloon. The volume of, say, 10 micrograms of gas, which is what our prototypes were producing, That would create a sphere of about 1.3 meters in diameter at 200 kilometers altitude. You're going to need more gas than that to inflate the balloon. I'll wrap it right up. There's a toxicity limit, but it's very low, and we're not worried about it being harmful. As far as safety, it's in your car's airbag, so it doesn't. It's been well tested and stable. As I said, it's a user-friendly plug-and-play system, and it won't provide additional debris risk because the balloon on its own would naturally decay quickly. In conclusion, we have a low-cost, effective, redundant, and low-impact design. Our goal is to reach TRL 5 by next summer. And lastly, I'd like to acknowledge my funding source, NASA, through STMD's SSTP, and they're my collaborators at Arkansas, as well as my collaborators at NASA. Thank you.
Thank you very much for the presentation. So it's time for questions.
I'm a bit worried about the vacuum tight seal between the balloon and your gas generator, but you mentioned that as well, that you think you have a solution for that. Just a question about the outgassing of the crystals, the sodium azide. Did you look into that? Will they outgas if not heated?
To my knowledge, no, not unless they're heated very near their decomposition temperature.
What is that temperature?
325 C. So if you get that hot on accident, your CubeSat's gone. It's dead anyways. So.
Yeah, but just from the sun, it may heat up to 100 degrees.
So I did one test. I left. Don't do this; it's bad for your hot plate. I left a beaker of it on a hot plate on about 150 C for a month, and couldn't detect a change in mass.
Okay.
That was my my quantitative test to do.
Just a final observation. You said that the orbit period will increase, will decrease. It's negative. dPdt is negative. But that means you go to higher altitude. Your orbit period your orbit period should decrease for the lower altitude.
Correct. I know what I did wrong there. It's because I have two negative signs. I have this negative sign and this negative sign. So I should have only had one. I apologize.
Okay.
What if there is a leak in the balloon? Would it inflate?
If there's a leak in the balloon, I think it will inflate. And there's a couple reasons why. First, the pressures we're talking about are very low in order to inflate it. So if you have a low pressure, you have a low leak rate. So even if we do have a leak, we can generate far more gas than we need to inflate. So even in the presence of a leak, I believe we can still inflate it. Then over time, if we have a continual leak, we have the option to keep inflating. So that's my answer.
The cost, it didn't look realistic to me because this is it's nice but very complicated system, and fabrication and such, it requires special machinery.
So that's a good point. I put the literal cost of making that device. At the University of Arkansas, we have a microfabrication center. I get billed out at $45 an hour to use their equipment, and it takes about 12 hours to produce a wafer, which has 60 devices on it. So the economy comes from the fact that you can have many devices on a wafer. If you wanted to, so I guess the cost I'm calling is price per unit, not necessarily price per run. The price per run would be more like $1,000. The rest of the cost, the components are pretty low cost. We use PIC microcontrollers, just standard FR4 PCBs, and we're going to manufacture the aluminum in-house.
It will be more than 500, not too much.
If a customer wants to buy it, say you want to buy it from one of your CubeSats, I probably couldn't charge you $500, but it's not going to be $20,000. So I recognize your point.
Well, why didn't you use some stiff material to keep the shape of balloon?
We didn't explore that with very much depth, but the short reason why is to keep the mass and volume envelope as minimal as possible.
But if you design such a way, then you must require the module to survive for a long time to complete the deorbit.
So if you want to complete the deorbit in, so I guess two points. One, the deorbit time that we're looking at is less than a year. Not unreasonable to think that it can survive. If we want to go to higher altitudes, you're absolutely right, it will need to last longer. But one thing to consider is if we successfully deploy the balloon, even if it gets a hole in it and leaks, it still has a significant amount of surface area that is not going to go away. It's not going to be as efficient, absolutely. But just the fact that we have a large balloon unfurled behind the CubeSat will significantly impact the orbital lifetime. So if we need to, let's say, have our orbital lifetime be decayed, say we're going to be at a 45-year limit, and we need this system so that we can be under 25 years. Even if, let's say we design it so it's going to deorbit 5 years, and then it fails completely, the addition of that extra material and surface area will bring us under the 25. And that's something we would do a lot more analysis on if we're going to make a flight unit. This whole campaign is going to give us all the information we need to make those calculations and make sure we stay in the safe margin.
Thank you.
Sorry, we don't have time for question, so we. No, the viewer has a priority, but I already. So please, if you have questions, ask the speaker.
Please come find me.
Okay, we'd like to thank again our speaker.